Hi there, I'm Jim Zirin. Welcome back to more Conversations in the Digital Age. Our show is about science on the march for the benefit of humanity. The Rockefeller University is a New York gem located on a 14-acre campus overlooking the East River on the Upper East Side of Manhattan. Founded in 1901 by John D. Rockefeller Sr., it is a world-class center for biomedical research, offering postgraduate and postdoctoral education. It boasts the highest number of Nobel Prizes in relation to research personnel in the world. Pretty impressive. In the course of its history, Rockefeller researchers have been at the forefront of the battle against autoimmune disease, heart disease and stroke, infectious diseases, cancer, HIV, AIDS, and neurological disorders such as Alzheimer's, the terrible afflictions we are all so worried about. Rockefeller is now in the midst of a $400 million expansion project needed to modernize laboratories and attract new talent. We're honored to have with us the president and guiding spirit of the Rockefeller University, Dr. Mark Tessier-Lavigne, who is in the best position to tell us what's new at this amazing institution and what is going on in biomedical research today. Mark, welcome to the program.
Thank you very much, Jim.
Now, perhaps you could fill in a little bit about the background and history of the Rockefeller University, because it is quite interesting.
Well, it is, as you mentioned, it's been around for over a century, founded in 1901 by John Rockefeller himself, who at the time was convinced by his advisors that there was a need to invest in biomedical research. At the time, very little biomedical research was actually happening in this country, and it was one of the first institutions devoted to trying to advance knowledge of fundamental biological mechanisms and then apply that knowledge to tackle poorly treated diseases. It started as a research institute, rapidly became a leading institute not just in this country but internationally. In the 1950s, it added a graduate program, so graduate students, and thereby became a university, and has gone from strength to strength over the decades. We have about 1,200 scientists on campus, divided into 77 laboratories covering the whole of biomedical research, 1,800 people total on campus. We have a 14-acre campus on the Upper East Side of Manhattan, and really Rockefeller has established itself as the leading biomedical research university based on the activities of our extraordinary scientists and also the culture of excellence that's been fostered there over the years. So we're very excited.
Now, you've used the term a number of times, biomedical research, and those in the audience, our viewers, may not know exactly what biomedical refers to. Perhaps you could define it for us.
Right, so we use the term biomedical to encompass two things. First, driving an understanding of the body in health and the body in disease at a fundamental level, understanding cellular processes, molecular processes, and then how they translate into the body's functions at an organismal level, how the heart works, how plaque accumulates in your arteries, how the brain functions, and what goes wrong in diseases like cancer and immune disorders. So it's biology applied to medicine, hence biomedical.
Now, is there a hospital that's part of Rockefeller University?
Absolutely. The Institute was started in 1901. In 1910, and this was very forward-looking, the Institute added a research hospital that was the first clinical research center in the U.S., focused on studying human biology. As you know, many biological sciences study laboratory mice or fruit flies, model organisms, because it's what you can study in the laboratory. We think those are extremely powerful. Our scientists use those tools, but just as important is to study human biology directly, and for that the research hospital serves that purpose. It's there really to study, again, how the body normally functions and what goes wrong in various diseases that remain poorly understood and poorly treated.
Now, how many students are there on campus?
We have 200 graduate students on campus of the 1,200 scientists total. So we're very focused and small. But the whole philosophy of the university is to stay small, but to punch above our weight. So the culture is a culture that's driven our scientists to excel across the board, which has led, as you mentioned, to a high level of accomplishment, including more Nobel Prizes in medicine or chemistry than any other institution in the world.
How many Nobel laureates are on the campus of Rockefeller University today?
Well, today we have 5. Over the century, 24, and again,
24.
That puts us ahead of any other institution out there.
Now, you have no undergraduate students.
No undergraduates, and again, it's a research institution. It's a research university, and so our graduate students are there to be trained and to do research, working with the postdoctoral fellows and the faculty and the other scientists who are there. So our mission really is a research mission. Our motto, of course, is science for the benefit of humanity. It's scientific research to uncover the mysteries of the body and apply that knowledge to help people.
And how many PhDs do you graduate each year?
About 25 to 30. The PhD students are on campus typically 5 or 6 years for their training.
5 or 6 years. And the postdoctoral students, they get no degree, they just continue their studies.
That's right. It's in biological, biomedical research, it's quite standard for people to get a PhD. That's their first wave of training. But that's usually not sufficient for them to be fully equipped to sally forth on their own and direct their own research program. So most people then do a second phase of training, postdoctoral, after they have their PhD. And there we have about 400 postdoctoral fellows on campus.
Do you charge tuition?
No, our graduate students are fully supported. There's no tuition, and actually we cover their living expenses as well. We want them to be able to focus. First of all, we want to be able to recruit people solely based on talent, so we don't want there to be any issues of access. And secondly, we want our students to be able to focus 24/7 on their research mission.
So how are you funded?
Well, a combination of the faculty raising money from many sources, including the federal government, the National Institutes of Health, as well as private foundations. We have a sizable endowment that really helps with university operations, and we do ongoing fundraising as well to support our programs.
Now, who is doing the research on campus? Is it solely the faculty, or is it the students as well?
Well, it's all of the scientists, and again, the scientists are all affiliated with one of the 77 laboratories on campus. So graduate students and postdoctoral fellows will be members of a laboratory headed by a faculty member, a professor, and the professor really sets the direction for their team, determines the scientific focus, raises the money to make that possible with help from the university, trains the students and the postdoctoral fellows. But the students and the fellows, of course, are very seasoned and very independent, and so it's mutually beneficial. The professor will train them in how to do science and help them with a new research direction, but they will be the source of many of the ideas and the creativity in the lab. So it's a very powerful synergy.
So what does a professor's day look like? Is the professor teaching all day, or is the teacher doing research all day?
The major focus of our faculty is research. We teach, our teaching is restricted to teaching graduate students, and it's almost an extension of the research mission as well. So that ends up being a real but focused part of their daily activity. Most of what they do is to focus on doing research with their teams, but also more and more of science, of course, is interdisciplinary and requires interacting with others as well. So they will interact with other scientists at Rockefeller and indeed at other institutions.
So does this involve lectures, or does it involve labs, or is it a combination of both? Or how are you taught to be a researcher? Well, other than innate curiosity.
That's right. Well, the research itself, of course, involves choosing an area of research. Let's say it's some aspect of neuroscience, how the brain works. You have to have an experimental system, and you focus on developing specific hypotheses about how the system works, and then performing experiments to test those hypotheses, which involve experimental manipulation. So a graduate student working in a laboratory will learn how to do experimental manipulations in the system that's been set up by the head of the laboratory, but they'll be expected to come up with their own ideas and to pursue them as well. So it's a constant cycle of thinking of the next experiment, performing it, getting the results, and reassessing based on that which way to go. That's the day-to-day of a graduate student, a postdoctoral fellow. Of course, for a professor, they will be spending a lot of time mentoring the students and postdoctoral fellows, going over the data with them, and critiquing the research results. The team will come together to do that as well. It's a very interactive kind of activity within a laboratory.
Now, my conception of a university is that a professor reports to another professor who reports to another professor who reports to the head of the department. The head of the department reports to some administrator, and then eventually you have the president up there at the apex. Now, at Rockefeller, they don't quite do that, do they?
No, we sort of have exactly the opposite. We have a very flat structure. All 77 faculty members report directly to the president, which
that's
of course,
you.
That's me, which at some level is absurd, of course, but it actually works. I don't do it alone. There's a vice president of academic affairs, chief of staff who take care of many of the academic or administrative issues. But by having that flat structure also, it means that, again, our faculty are freed up to just focus on their research. You don't have all of the requirements that come with being part of the departmental structure and all that reporting. What we really aim to do is to free up our faculty to focus on the research. The other aspect of not having a departmental structure, as you described, which is standard, is that we don't have silos. And so we are, by virtue of our structure, interdisciplinary. This is true in our recruitment as well. We have a best athlete model. We go for the very best scientists regardless of field. We hire the scientist.
But the field has to be biomedical research.
It has to be biomedical
within
research.
That field.
That's right. It could be cancer research. It could be neuroscience. It could be virology. It could be immune disorders. It could be structural biology or cell biology, genetics. And so we end up with situations where you have a neuroscientist whose laboratory is next door to an immunologist, next door to a structural biologist, and that promotes interactions across disciplines. And it's at those interfaces really that the sparks fly, that new ideas come, and that's what's enabled our scientists to be so far ahead of the curve on so many instances.
So as you look at Rockefeller today, are you weighted toward any particular discipline, virology or cancer research?
We actually cover most of the most fields of biomedical research. We do have, I'd say, probably the largest concentration of faculty is in neuroscience, and that reflects the fact that there are so many different facets of neuroscience, how the brain normally works, what goes wrong in neurodegenerative disease and psychiatric disease, and also because it's an exciting field that's breaking open. Probably the second largest concentration is in cancer, but name the field, we have people working in those fields.
Now, can you tell us something about the breakthroughs, the medical breakthroughs that have come as a result of research at Rockefeller University?
Sure. Maybe I could give you a few examples historically and then tell you about some of the more recent ones. If we, of
That'd
course,
be great.
There are so many that I could spend the next hour regaling you with tales of them, but maybe I'll just highlight a few. Historically, certainly, I think one of the most transformative of all was the discovery in the middle of the 20th century that genes are made of DNA. We all know the phrase, it's in your DNA. We know that DNA is the substance of heredity. It's what you inherit from your parents, and that means that you have many traits that are inherited from them.
Helps the cops detect closed cases.
Exactly, exactly.
Stale cases.
We've known that there were elements of heredity since the 19th century, but for the better part of a century, nobody knew what the substance was that encoded that hereditary information. And it's actually Rockefeller scientists who, in a 20-year-long odyssey, discovered that the substance of heredity is DNA. Very controversial at the time, and that was 1944. 9 years later, 1953, is when the structure of DNA, the double helix that everybody's familiar with, was discovered. Nobody would have thought to look for the structure of DNA if we hadn't known that DNA was the material of heredity. So very big discovery. Others, very rapidly, the discovery that viruses cause cancer, made at Rockefeller. The discovery of the development of triple combination therapy, antiretroviral therapy for HIV/AIDS, the development of methadone as a treatment for addiction, the discovery, recent discovery of the sentinels of the immune system. They're cells that have to detect parasites, bacteria, viruses that infect you, so that the immune system can attack them. And those specialized sentinel cells are called dendritic cells, discovered at Rockefeller University. Discovery of the appetite-regulating hormone leptin, recent discovery at Rockefeller. So those are all some of our historical discoveries.
So the way dendritic cells work is that if one is confronted with some sort of toxin, the dendritic cells detect that and then stimulate the immune system to combat whatever the invader is. Is that?
That's right. They will instruct the warriors of the immune system. They're called T cells and B cells. The T cells will go and attack the invaders. The B cells will make antibodies. You've heard about antibodies circulating in your blood. They're made by B cells, but they have to be instructed on what they should be targeting, and the dendritic cells do that.
Well, thank you for that. I think I'm ready to open a lab. Now, what are additional projects that you're working on now? What are the principal projects that you're performing?
The principal projects, I could take any of the 77 laboratories because our scientists are doing extraordinary work. But just to highlight a few, things that are really hot off the presses, cutting edge. Continuing with this theme of combating HIV/AIDS, existing standard of care, this antiretroviral therapy, holds the virus in check and makes it a chronic disease. But what we'd really like is to be able to eradicate the virus. Our scientists are working on that, and a first step actually is developing a complementary therapy, harnessing the body's own defenses, these antibodies. One of our scientists has been able to make antibodies that are broadly neutralizing to HIV. The problem here is the virus will mutate rapidly. So if you make one antibody, it'll escape it. But by finding parts of the virus that can't be mutated easily, these scientists have been able to make antibodies that attack the virus, and in clinical trials at the Rockefeller Hospital are showing tremendous efficacy that can be used in a complementary way to existing standard of care. Obviously, the long-term developing a vaccine to HIV is really the holy grail, but we hope that this might be one step towards that. Another area that fascinates me is, as a neuroscientist, which is my own background, is how the brain works, and specifically how we detect objects in the environment. A distinguished history at Rockefeller, one of our previous presidents, Torsten Wiesel, Nobel laureate, still active in the university, received his Nobel Prize for understanding how the visual system works. One of our current faculty members is focused on face recognition. So we know that recognizing faces is a very important aspect of our social interactions. And there are parts of the brain, it turns out, that are specialized in detecting faces. Our scientists, together with collaborators, identified the regions of the brain and show that there are 5 specific areas that are interconnected. They're involved in extracting features from the visual image to recognize a face as a face and learn the rules. We all know that you can't detect a face as well upside down as right side up, and he's been able to show how that arises in those centers. And in cartoon characters, you can recognize a face as a face just by virtue of having 2 eyes, a nose, a slit for the mouth, and a bit of a rounded shape around it. And it turns out there are cells in the brain that detect those features and that start assembling the face.
Something's telling me there's Mickey Mouse.
Exactly.
Looking forward to the future, what do you see as being in store for Rockefeller, both physically, because I know you are modernizing and slightly expanding your plant, and a $400 million project, and also in terms of areas that are at the frontier.
We're currently adding 2 acres to the 14 acres of the university by covering 4 city blocks of the FDR between 64th and 68th Street. There'll be a platform on that, and on that we're going to be putting a low 2-story building that's almost 3 city blocks long with interconnected labs. 600 scientists will be able to fit in that building. And it's the way of the future in science. Scientists want to be able to interact with other scientists. It's a very non-New York City thing to do. In New York, you put big towers. But the problem with towers is you interact with people on your floor, but not people on the other floors.
As few as possible.
That's right. With this design, the scientists will be able to just, walking down the corridor, interact with all of the other scientists. We're very excited by this. It will have a green roof, so it will add 2 acres of green space to the university.
But 600 labs, you're planning
600 people.
600 people. So you're planning on expanding your scientist population?
It's not an expansion, thanks for asking. It's an extension of the university, and it's really a lab renewal project. Labs don't age very well. And so we have some labs that are coming to the end of their useful life. This will enable us to move our scientists to new facilities that are essential for their work, and also to recruit the very best and the brightest. In terms of the fields that are exciting, again, we're in a golden age, Jim, of biomedical research, an explosion of knowledge of fundamental mechanisms, an explosion of our ability to take that knowledge and, based on that knowledge, develop therapies and cures for poorly treated diseases. And this is true across the board in cancer, where our scientists are doing work on DNA damage and its repair, on metastasis. It's the metastases, of course, that kill you in cancer. How it is that cancer cells migrate away from the primary tumor. We're starting to unlock some of those mysteries. Immunotherapy, harnessing the immune system to combat cancer. Whether it's in other infectious diseases, we've talked about HIV, but others are very much in the news. Ebola, of course. Neuroscience, big area, which is breaking open because of the development of new technologies that enable us to probe the brain's function. I talked about face recognition, but they're very powerful technologies, part of President Obama's Brain Initiative, that are enabling us to really understand how the brain works and what goes wrong in diseases like Alzheimer's disease and in psychiatric diseases.
In contemplating your expansion,
Yep.
You've also taken into account the community, have you not?
In planning this campus extension, we work closely with the community, with the city council and the community board. And also, one of the things we're doing is to enhance the East River Esplanade alongside Rockefeller. That's the path, of course, right next to the river. That's very popular for hiking and walking and biking. We'll be adding seating, landscaping, sound barriers, a dedicated bike lane. We're restoring the infrastructure also, the seawall. We've made a $1 million contribution to create an endowment to maintain the landscaping in perpetuity. So we work closely with our local community, the Friends of the East River Esplanade, to make that possible. So we're excited about that project. Also, a very strong focus on outreach to schools, elementary, middle, high schools, with a number of activities that bring students to campus. My favorite is in May every year. We have a day we call Science Saturday. 500 students and 500 parents and teachers come to our campus to do experiments, but that are set up as fun experiments that are accessible to kids, that get them excited about science.
Okay, so I think we have to wrap up, but I have a question for you.
Yes.
When do you imagine we'll find cures for the degenerative diseases, cancer and HIV, and also the neurological diseases like Alzheimer's?
Well, scientists never like to answer a when question because there are so many unknowns, but maybe I can give you a perspective. Our ability to combat cancer has accelerated dramatically in the last 25 years, since the discovery of oncogenes in the 1980s. It was that knowledge that propelled us forward year after year, decade after decade, and most recently you've seen the headlines about immunotherapy that are curing sizable subsets of patients who have metastatic melanoma, lung cancer, bladder cancer, and so forth. Very great advance. And I think we're going to go from strength to strength. This will be played out over decades, but I think we're making huge headway against cancer. Neurodegeneration is much further behind because our knowledge of what goes wrong has lagged, but that's accelerating now. I'd say, I don't want to be realistic. We're about 20 years behind with neurodegeneration where we are with cancer, but we're starting to see the knowledge advancing, that leading to therapies that are in the clinic right now. Hopefully some of them will yield fruit, but I'm very optimistic that if I count in decades, in the next 10 or 20 years, that we will have therapies for Alzheimer's disease, Parkinson's, Lou Gehrig's disease, and so on. And really the question is, how rapidly can we get there? Do we have to wait a decade or two? Can we accelerate that? And I think we're just investment limited at this point. I think the knowledge and the ideas are there. We just have to invest in those. So I'm very optimistic about progress across many fronts. Of course, we always have to inject a note of caution. Science is very uncertain. It advances erratically. But I think, as I said earlier, we're in a golden age, not just of biological discovery, but also of translating that knowledge into therapies and cures for these dreaded diseases.
Well, this is really wonderful. Optimistic about progress in a golden age. Mark Tessier-Lavigne, thank you so much for coming by.
Thank you.
And thank you for coming by. Tune in next week for more Conversations in the Digital Age. I'm Jim Zirin. All the best and take care.